So, the universe, it seems, we think we understand it, right? We have laws of physics that we study, and we create models. All of this is quite convenient. But this is just working with outdated data. What happens when a new, significantly more powerful tool comes along? I am talking about the James Webb Space Telescope, a true engineering marvel. This instrument has started sending data that simply does not match our expectations. And I do not mean minor discrepancies. I am talking about things that, according to our comfortable theories, should not exist. This data suggests that the fundamental principles on which everything is built may be incorrect. And yes, this is not a joke or a movie script. This is physics based on hard data. What we are observing now, thanks to the Webb telescope, is not just an update to our understanding of the cosmos. It is a potential signal that our entire system of the universe has a critical vulnerability. And when there is an error at the foundation of a system, let's say, it is not a trivial problem for future minds. Let's break this down. For centuries, humanity has sought to grasp the secrets of the universe. We have looked at the starry sky, trying to determine our place in the universe, its nature, and of course, its future. From the first cave drawings of stars and ancient Greek concepts of the cosmos, to Galileo's telescope and the Hubble Space Telescope, every effort has been driven by an insatiable thirst for knowledge and a desire to look beyond the horizon of the known. We are now on the brink of a new era, and all of this is thanks to the James Webb Space Telescope. This unique device, a true masterpiece of engineering, not only captures the light of ancient stars, but also reveals to us a past so distant that it predates the emergence of our planet and likely challenges our very notions of time and reality. In the year 2021, after many years of development, delays, and multi-billion-dollar investments, NASA, in collaboration with European and Canadian space agencies, launched the James Webb Space Telescope. Its tasks are incredibly ambitious, to provide answers to fundamental questions that have troubled scientists for centuries. How did the first galaxies form? What lies beyond the boundaries of the observable universe? And perhaps the most thrilling question, are we alone in all this cosmic splendor? Unlike its predecessor, the famous Hubble telescope, which operates primarily in the visible and ultraviolet spectra, Webb specializes in infrared radiation. Why is this so important? Imagine that the universe is filled with dust and gas, visible light, like the headlights of a car in thick fog, is scattered and absorbed by this cosmic veil. Infrared radiation, on the other hand, can penetrate through this dust, acting like thermal imaging devices and allowing us to see objects that are inaccessible to other telescopes. In addition, during the expansion of the universe, light from the most distant and ancient objects is stretched, shifting into the infrared spectrum. This means that the James Webb Space Telescope is effectively observing the redshift of light from the earliest stars and galaxies, allowing us to glimpse the earliest epochs of the cosmos. At a time when the universe was only a few 100 million years old, it is akin to a time machine that transports us to the dawn of the universe. Thanks to this unique technology, Webb has already made discoveries that have caused scientists to reconsider many previously accepted theories. These discoveries are so impressive that they evoke not only admiration but also some concern. However, let us not get ahead of ourselves. The main question regarding how these discoveries relate to the end of the universe still awaits exploration. We are slowly but steadily moving toward it. For now, let us focus on the first and most shocking discovery that literally shook the scientific community and raised questions about the fate of our universe. In the very first months of the James Webb Space Telescope's operation, truly astonishing results were obtained. Among the many images of distant space transmitted to Earth, researchers were particularly struck by 6 gigantic galaxies that formed only 500 to 700 million years after the Big Bang. Imagine that the history of the universe is compressed into one day. These galaxies would have formed within the first 30 minutes. This discovery marked a significant breakthrough for modern cosmology. Why? Because according to previous understandings of galaxy formation, this process was expected to occur slowly and take billions of years. The cosmological model we use is known as the lambda cold dark matter model, or the standard model of cosmology. It suggests that the early universe, which was a chaotic jumble of gas and radiation, needed to undergo billions of years of evolution before ordered structures, such as massive galaxies similar to our Milky Way, could emerge. This process begins with small clumps of dark matter that gradually attract gas, form the first stars, and then merge into larger structures. It is similar to how a small stream eventually becomes a river and then a powerful waterway. However, these 6 galaxies not only formed significantly earlier than expected, but also exhibited incredible structural complexity and mass. They were as large and developed as galaxies that, according to our understanding, should have appeared much later. This can be likened to a situation where, if you were to travel back to the early era of human civilization, for example, during the time of the first agricultural settlements, you would find already constructed skyscrapers, high-speed railway networks, and modern metropolises. This simply does not fit into the overall picture. A logical, even glaring question arises. How could such gigantic galaxies have formed so rapidly? This discovery not only calls into question existing theories about the origin of the universe, it raises concerns about the accuracy of our physical laws and our understanding of cosmic evolution. Scientists around the world are actively studying new data, formulating hypotheses, and engaging in discussions about possible interpretations of this anomaly. Several assumptions are being considered in scientific circles, each striving to explain this mystery, and each one is intriguing and possibly alarming. The first hypothesis concerns a new role for dark matter. We know that dark matter is an invisible substance that makes up about 85% of the mass of the universe, and it plays a key role in the formation of galaxies. It serves as a sort of gravitational framework around which ordinary matter accumulates. But what if its functions in the early universe were different from what we assumed? Perhaps there are unknown interactions of dark matter that significantly accelerated the process of gas compression and star formation. It is possible that dark matter did not simply passively attract matter, but possessed an active mechanism that rapidly created massive structures. This could indicate the existence of entirely new hidden physics that we are just beginning to explore. If this physics is indeed so powerful, what else might it reveal? The second hypothesis concerns a potentially incorrect timeline of the universe. What if all our notions of the age of the universe are not entirely accurate? If these galaxies existed a long time ago and were already developed, perhaps the Big Bang did not occur as we imagine, or cosmic time is not as linear as it seems. This could mean that the universe is older than we think, or that it expanded at completely different rates in the past. Some radical theories even suggest that the Big Bang was not the beginning of everything, but merely a stage in a larger cyclical process in which our universe is born and dies repeatedly. If this is the case, then our calculations of the age of galaxies may have been incorrect, and we are simply observing old galaxies in the early universe. But then the question arises: what was happening before the Big Bang, and how does it affect our existence now? The third hypothesis is the potential evidence for the existence of a multiverse. This is perhaps the boldest and at the same time the most enticing assumption. What if these enormous galaxies are not the result of errors in our models, but simply do not belong to our universe? If the James Webb Space Telescope is detecting signals from beyond the reality we know, this could become the first experimental confirmation of the existence of a multiverse, in which our universe is just one of countless bubbles in an infinite cosmic ocean. Imagine that each universe may have its own unique physical laws, its own rates of matter formation, and its own timelines. If we had the opportunity to glimpse into another universe where time operates under different laws or developmental processes occur significantly faster, It could explain their inaccessibility to our perception. But if we are capable of observing other universes, there is a possibility that they can see us as well. And if such worlds truly exist, and our physical laws do not apply there, how might this affect the stability of our own universe? How could these mysterious galaxies threaten the existence of our reality? We are approaching an answer, but to do so, we must delve into the most hidden forces of the cosmos. These forces make up 95% of all that exists, yet they remain invisible to us. Understanding this is crucial for forming a holistic view of the universe. To unravel the mysteries of these unimaginable galaxies and their connection to the proposed cosmic light, it is necessary to deepen our study of the enigmatic components of the universe, such as dark matter and dark energy. Our current understanding of the universe is based on the objects we can observe and measure: stars, planets, gases, dust, and galaxies. All this visible matter constitutes only a tiny fraction, about 5%, of the total mass energy content. The remaining 95% remains unseen, immeasurable, and represents a complete mystery. This can be compared to an iceberg, where we see only its tip, unaware of the 90% of mass hidden beneath the water's surface. It is these hidden elements, dark matter and dark energy, that are the true architects and possibly destroyers of our universe. Let us take a closer look at dark matter, the invisible glue that binds galaxies together. The idea of dark matter is not new. Its existence was first proposed in the 1930s by Swiss astronomer Fritz Zwicky. While studying the motion of galaxies in the Hydra cluster, he noticed something strange. The galaxies were moving at such speeds that they could not be held together by only the visible gravity created by stars and gas. It resembled the rotation of an object that should have been flung away due to centrifugal force, yet for some reason, they remained in their orbits. Zwicky suggested the existence of an invisible substance, which he called dark matter, to explain this phenomenon. His bold hypothesis initially met with skepticism. However, after several decades, his ideas gained confirmation. Although we still cannot directly observe dark matter, its existence is supported by numerous indirect data and its gravitational effects on visible matter, as well as its influence on the motion of galaxies. As Zwicky noted, galaxies rotate faster than would be possible if they consisted only of visible matter. The rotation curves of galaxies, which show the relationship between the speed of stars and their distance from the center, demonstrate that the outer regions of galaxies rotate almost at the same speed as the inner regions. This is only possible if there is a vast invisible cloud of dark matter that keeps the stars in their orbits. Without dark matter, galaxies would simply break apart. The distortion of light, known as gravitational lensing, occurs when light from distant objects passes through large clusters of dark matter and bends in the same way that light changes direction when passing through a lens. This effect, called gravitational lensing, allows astronomers to create maps of the distribution of dark matter in the universe, even though we are unable to see it. We observe distorted, elongated images of distant galaxies, which testify to the presence of enormous invisible gravitational fields that play a key role in the formation of the universe. Furthermore, the standard cosmological model asserts that without dark matter, galaxies and large structures in the universe could not have formed. In the early days, when the universe was extremely hot and dense, ordinary matter was too widely dispersed by radiation to begin condensing. Dark matter, which does not interact with radiation, could start to clump together into dense formations under the influence of gravity much earlier, creating gravitational collapses into which ordinary matter then flowed, forming the first stars and galaxies. It acted as the invisible seeds for future galaxies. Now we come to an important point. It is possible that dark matter played a crucial role in the formation of those unusual galaxies discovered by the James Webb Space Telescope. If standard models of galaxy formation do not hold, it could mean that dark matter in the early universe behaved in a completely different way than we had assumed. Perhaps it possessed unknown properties that allowed it to gather matter incredibly quickly and form massive structures. This may indicate the existence of hidden physics that governed the early universe and is fundamentally different from what we observe today. If this physics is so powerful, what else might it be capable of? Could it, for instance, destabilize space-time itself in anticipation of an end? If dark matter is the glue that holds the universe together, then dark energy acts as the force that tears it apart. This is one of the greatest mysteries of modern physics. Many scientists believe that it holds the key to unraveling the ultimate fate of the universe. In the 19th and 20th centuries, one of the most astonishing discoveries in cosmology took place. Scientists studying distant supernovae, explosions of massive stars that serve as standard candles for measuring cosmic distances, discovered something completely unexpected. They assumed that the expansion of the universe was slowing down under the influence of gravity, similar to how a stone thrown into the air slows its flight before falling. However, instead, they observed that the expansion of the universe is not only continuing, it is accelerating. This was absolutely paradoxical and did not align with any known physical laws. To explain this phenomenon, a hypothesis was proposed regarding the existence of an invisible force that pushes the universe outward, akin to some form of anti-gravity inherent to space itself. This force was named dark energy. According to modern estimates, dark energy constitutes approximately 68% of everything existing in the universe, making it the primary component. How does dark energy relate to the unimaginable galaxies discovered by James Webb and to the fate of our universe? If dark energy truly accelerates the expansion of the universe, it may imply that its influence was significant even in the early times, perhaps even more powerful than we had assumed. And if it already possessed such strength that it contributed to the rapid formation of massive structures, possibly creating conditions for the accumulation of dark matter, this suggests that its impact continues to grow. However, let us consider more troubling assumptions. If dark energy is a property of space-time itself, then as the universe expands, more space is created, and thus, more dark energy. This could lead to a scenario that scientists refer to as the Big Rip. If dark energy continues to grow without limits, its repulsive effect will become so immense that it could overcome all other forces in the universe, including gravity and electromagnetic interactions that hold atoms together. If our universe is not the only one, and there are many universes with different physical laws, then the discovery by James Webb could be the first evidence that our universe is not unique. This raises exciting and frightening questions. And if the telescope has captured the light from galaxies that contradict our physical laws, could it also detect light from another universe? Are there places where gravity and other physical laws operate entirely differently? If such laws manifest in our universe, what then will happen? Perhaps the impossible galaxies are not just an anomaly, but an early sign. A sign that dark energy was much more active in the early epochs than we thought, and that its accelerating influence could lead to catastrophic consequences. If these galaxies are the result of extremely rapid growth, driven by the powerful influence of dark energy in those ancient times, then this could be the first signal that this force is not merely expanding the cosmos, but actively tearing it apart. But that is not all. How exactly could this rupture lead to the end of the universe, and how inevitable is this scenario? We will discuss this in the concluding, most intense part of our exploration. Now, friends, we are approaching the climax of our journey through cosmic mysteries. We have already established that the James Webb Space Telescope has revealed impossible galaxies in the early universe, which challenge our current cosmological models. We have also delved into the study of dark matter and dark energy, the invisible forces that shape and destroy our universe. It is time to bring all these aspects together and answer the main question. How could these discoveries lead to the demise of the universe? The James Webb Space Telescope. not only compels us to reconsider our understanding of the past, but also raises important existential questions about the future of the cosmos and our place within it. What will be the ultimate state of the universe? Are we heading towards infinite expansion, catastrophic contraction, or something more astonishing, perhaps even terrifying? Scientists have proposed several key hypotheses regarding the fate of the universe, each with its own implications for all existence. The first scenario is the Big Freeze. This is the most likely outcome if dark energy continues to accelerate the expansion of the universe. In this case, in the distant future, galaxies will be so far apart that light will not be able to travel from one to another. The sky will become completely black and lifeless. The universe will turn into a cold and lonely space, where stars will extinguish after exhausting their fuel supplies, becoming white dwarfs, neutron stars, and black holes. Then, black holes, slowly evaporating through Hawking radiation, will eventually vanish. The universe will reach a state of maximum entropy, a complete absence of energy for work, where even atoms will be in a state of absolute stillness, separated from one another by unimaginable distances. This will be a slow but inevitable death from cold and solitude. The next scenario is the Big Crunch. This is a more dramatic development. There is a possibility that dark energy may change its behavior in the future. It may prove to be unstable, its influence weakening or even reversing. In this case, gravity, which constantly attracts matter, will eventually begin to slow down and then reverse the expansion of the universe. Galaxies, instead of flying apart, will start to come together, colliding with one another in a grand cosmic catastrophe. Temperature will rise, space-time will contract, and the entire cosmos will collapse back into a single point of infinite density, a singularity, similar to that which existed before the Big Bang. This scenario implies a cyclical universe, where the end of one universe may become the beginning of another in an endless cycle of birth and death. It will be a kind of cosmic reboot. The third scenario is the Big Rip. This, my friends, is the very scenario that may be directly linked to the discoveries of the James Webb Space Telescope and inspires the greatest dread. If dark energy continues to expand actively, its density will increase, and the repulsive force will become so powerful that it could overcome all other forces in the universe, including gravity, electromagnetic interactions, and even the strong nuclear force. Initially, the expansion of the universe will accelerate to such an extent that it will destroy even those structures held together by gravity. Galaxies will begin to disintegrate, followed by star systems and planets. After that, the wave of destruction will reach atoms. Electrons will be ripped away from nuclei, and atomic nuclei will break apart into elementary particles. Ultimately, the very fabric of space-time will be torn apart, transforming into an unimaginable vacuum in which nothing will remain, neither matter, nor energy, nor even space itself. In this scenario, the universe will not simply disappear, it will be completely destroyed, torn apart by its own energy. This is where we reach the climax of our story. How can the discoveries of James Webb foreshadow the Big Rip, threatening the very existence of the universe? These most unexpected galaxies discovered by Webb, which formed at an incredible speed and possessed colossal mass in such an early universe, may hold the key to the puzzle. If standard models of galaxy formation do not explain their existence, it may mean that dark energy had a much more powerful effect back then than we believed. If its influence was so great in the past, facilitating such rapid and massive structural formation, this could serve as an early warning. It suggests that dark energy is not merely expanding the universe, but that its density and power are steadily increasing. If the density of dark energy continues to rise, this will lead to the repulsive force becoming ever stronger, accelerating the expansion of the universe to catastrophic scales. The discovery of these anomalously massive mature galaxies in such an early epoch may indicate that dark energy is not constant. Perhaps it not only exists but also intensifies over time, or its properties in the early universe were radically different from what we assumed. If this is the case, and its strength continues to grow, then the scenario of the Big Rip, where nothing remains, not even the tiniest particles of matter, becomes not just a hypothesis, but a real and inevitable prospect. Imagine that just 500 to 700 million years after the Big Bang, such colossal structures already existed. This indicates extremely aggressive and rapid formation, but what is happening now, 13,800,000,000 years later? If the aggression of dark energy continues, we may be on the brink of a moment when it finally tears apart everything that exists. Webb's discoveries compel us to rethink fundamental constants and laws. If these galaxies are the result of an extremely rapid growth, driven by the powerful influence of dark energy in those distant times, it may be the first signal that this force is not just expanding the cosmos, but actively tearing it apart. If the speed of this rupture continues to increase, our universe will not just die, it will be shredded into pieces, torn into the smallest particles, leaving nothing behind. No stars, no planets, not even atoms. Regardless of the final outcome of the universe, there is one undeniable fact. We are here and now. Our ability to ask questions and strive to understand the world around us is already something incredible. The James Webb Space Telescope unveils the veil over the past and future of the universe, but only we can decide what to do with this knowledge. If the universe is indeed expanding, will we ever learn to travel through it? If parallel universes exist, will we be able to explore them? The great truth of the cosmos lies not only in its variability, but also in the fact that we are changing as well. With each new discovery, we realize that our understanding is just the tip of the iceberg. The findings of James Webb challenge our perceptions of reality, prompting us to ask even more questions. Perhaps the most astonishing mysteries of the universe are yet to be revealed. And who knows what else this amazing telescope may show us? What new challenges will it present to our understanding of the universe? So, friends, we started with the question: could the latest discovery of the James Webb Space Telescope threaten the existence of the universe? Now you understand that the answer is not as simple as it seems, and not as straightforward as one might hope. The unusual galaxies discovered by Webb in the early universe may turn out to be not just anomalies, but ominous portents. They may indicate that dark energy, this mysterious force destroying the cosmos, is acting much more aggressively than we had assumed. If its power continues to grow, the scenario of a big rip, where nothing will withstand, not even the smallest particles of matter, will become quite real. So what awaits us? Doom? Or are these discoveries merely a step toward a deeper understanding of the universe that will allow us to find answers and perhaps even influence our fate? We will discuss this and much more in upcoming episodes. For now, ponder this. We live in a universe that is not only expanding, but possibly actively tearing itself apart. Our telescopes, peering into its past, send us alarming signals about the future. What do you think about these discoveries? Is James Webb a harbinger of not only new knowledge, but also fatal warnings? Share your thoughts, and see you soon.